Hello, welcome to my channel Chemical Chemistry Classes. Today we're going to start a new chapter, that is Organic Chemistry. Some basic principles and techniques, Unit 8, Class 11 NCERT. Let's start this chapter and first discuss what is organic chemistry. Organic chemistry is the branch of chemistry that studies the structure, property, composition, reaction and preparation of carbon containing compound, mainly focusing on those covalent bonded in carbon atom, excluding carbon oxide and carbonates. Carbon always surprises us. Based on its electronic configuration, it seems like it should only form divalent compounds, right? But in reality, it almost always shows tetravalency. The secret behind tetravalency lies hybridization. Hybridization, we can say that this is a clear or clever rearrangement of orbitals so carbon can bond in a versatile ways. So as we all know that the configuration of carbon is 1s2, 2s2 and 2p2. At first, this means that carbon has only two unpaired electrons, so it should form only two bonds, right? But in reality, we see it forming four bonds. Like we can take one example, like methane, right? So how does carbon pull off this trick? How carbon show tetravalency? One electron from 2s orbital gets promoted to the empty, as we all know, like in p, this is orbital structure is like this, like in 2p2, this is the arrangement of orbitals in this situation. But what happens is that one electron from 2s orbital gets promoted to empty 2p orbital, and now carbon has four unpaired electrons and their electronic configuration is 2s1 and 2p3. So this is just the starting point of tetravalency. Hybridization. Let's take and imagine a situation where carbon act as a diesel mixing track. Like instead of using their orbitals separately, it it hybridize them. The s and p orbital combine into new and identical orbital, and that is called the hybrid orbital. If carbon mix 1s and 3p, that means 1s and 3p orbitals, you get sp3 hybridization, that is tetrahedral, and their bond angle is 109.5 degree. Like we can take one example, that is CH4 methane. If carbon mixes agar carbon ने 1s orbital with 3p and we get sp3, when carbon mixes only 1s orbitals and 2p orbitals, we get sp2 hybridization, and that is trigonal planar 120 degree angle. We can take example like C2H4. If carbon mixes 1s and 1p orbital, you get sp orbital. If carbon get 1s and 1p orbital, and we get sp hybridized orbital, and this must be linear and bond angle is 180, and like in C2H2 is one of their example, right? So hybridization in carbon is a superpower. Kuch reasons, based on some reasons, that is stronger bonds. Since hybrid orbital overlap better than pure orbital, as we all know, right? Hybridization give them different geometries like tetrahedral, planar, linear, the ability to form single, double and triple bond. So no wonder carbon is called the backbone of organic chemistry. Its ability to remix orbitals explain why it forms millions of compounds, far more than any other element. So this is the reason of the tetravalency of carbon. So as you all know how we get sp, sp2, sp3 orbitals. Next is the features of pi orbitals, right? A covalent bond is really just atom shaking hand, right? In covalent bonds, that means they are going to share electrons are going to share, but the handshake happens through the overlap of orbitals. And how they overlap, that decides the type of bond and its strength. Like when two atomic orbitals form different atoms come close, they are from different atoms and they come close and overlap and they form new orbital. This shared orbital is called localized molecular orbital because it belongs to both atom and not just one, right? So this is what, this is the sigma bond, right? So when head to head overlap, like means when like two people pressing palms front to front, like they are just head to head overlap, that's form the sigma bond. And this is the strong and lies directly between the nuclei. And side to side overlapping means they form pi bond, right? In pi bond what happened, they used to just sidewise overlapping, right? So they just overlap side to side and we call side to side overlap. I will show you with one example like this. This is one of orbital, right? This and this no longer one, and this. Like when they form this bond, they are pi bond, and this is what, this is sigma bond. Now you understand better, right? So in side to side overlap forms a pi bond. This is usually weaker than sigma bond because the sideways overlap is less effective. Pi bonds never exist alone, they show up alongside a sigma bond, right? So we must understand another concept, like there is some sign of orbital like positive and negative, right? A positive or negative, there is a sign, right? So orbitals, they are like waves, right? In phase, out phase, like so when you add waves, if both waves are in same direction, when we are going to add some waves, if the waves are in the same direction, same phase, they have same sign, they reinforce each other and this increases electron density between the nuclei and they forms the bonding molecular orbital that is more stable and they have low energy. What is this? Is a bonding molecular orbital, right? So if waves are in opposite direction, okay, when you add, they are in different direction, they are in different sign, they are in different phase, they cancel out, creating a node. With node means there is zero probability region. Node is what? Node is a zero probability region. So this forms an anti-bonding molecular orbital, and anti-bonding molecular orbital is what? They are unstable, they are have high energy. So the bond formation depends on where electrons like to hang out, right? So in bonding orbital, what happen? More electron density between atoms and they pull nuclei together and they're stable and low energy, right? So in bonding, energy is low but they are stable. And in antibonding, what happen? There is less electron density, nuclei repel each other, they are unstable and they have high energy. They are not in low energy. So every stable covalent bonds you see exist because nature prefers bonding orbitals over antibonding orbital. The strong overlap lowers the system energy, and which is why molecule forms in the first phase, right? So this is all about the pi bonding, sigma bonding, bonding molecular orbital, anti-bonding orbital. This is all about, right? So next is the structural representation of organic compound, right? Like organic compounds can be drawn in different, or we can say several ways are there, on how much detail you want to show. That depends the most. So each style of structural representation give us different insight about bonding, electron pair, connectivity. So let's understand all this. First is Lewis dot structure. And what happened in Lewis dot structure? Shows this shows all electrons, like so bond pairs also, lone pairs also, and each covalent bond is drawn as two dots. This time they are shown like two dots, right? So like in H2 we get this, like so. This is very accurate but gets very messy. Dash structure hota hai where one dash represents single bond, double dash represent double bond, triple dash represents triple bonds, and lone pairs on atoms may or may not be shown in dash structure. In condensed structure, what happened? That's atom bonded to carbon are immediately next, right? Immediately next. So kya hota hai? Shows that bond shows implicity without writing every bond. In bond line, what we get, carbon atoms are not written, they are represented by corners and ends of line. Space filling hota hai, ball sticky models that focus on the connection between also the geometry. So there are more structure, right? So we can take one example. We understand in dash structure what happened. When there is a single dash, there is single bond, double dash shows double bond, triple dash means triple bond, right? So there are different types of structures we can show here. Like in ethane, what happened? This is the structure of ethane, right? In ethene, this is ethane. In ethene, what happened? There is a double bond, and this and this and this. This is the structure of ethene. And ethyne, there is a triple bond like this, and this is the what? This is linear structure. So this structure formula can be further omitting, or all of them represent dash. As we can write ethane like this, and we can also write ethane like this, right? We can write ethyne like this, and we can also write ethyne like this. We can write ethane like this, and we can also show ethane, like this, right? So there are very different ways that varies, like so. We can also show in bond line structure representation of organic compounds where carbon and hydrogen atoms are not shown, and the lines representing only carbon bond through a zigzag fashion, right? So we can also show you some zigzag fashion like this. We can take one example like 3-methyl octane. 3-methyl octane. And this is their structure. We can show 3-methyl octane in this way also, and this way also, and this is a terminal representation. We can write like this also. The terminals represents methyl group. So there is also various ways for representing 2-bromobutane like this, and we can also show 2-bromobutane by this, like Br idhar aayega. This is 2-bromobutane. In cyclic compounds also, the bond line formulas are also given. Like in cyclopropane, we can write this structure, cyclopropane, or we can write like this also. This is also cyclopropane. In cyclopentane, The structure of cyclopentane is like this. And we can write like this. This is what? This is cyclopentane, right? So this is the different ways for representing the structures of organic compounds. Next is three-dimensional representation of organic compound. Three-dimensional representations of structures of organic molecules can be represented on paper by using certain convention. We can show 3D structures on paper also, but that's all depends upon the structure of molecule and how we will represent this. For example, we are using this solid one. This solid one, right? This solid one is for solid bond, and this like solid, and this is what? This is the dashed wedge formula. Okay. So the 3D image of the molecule form a two-dimensional picture molecule, right? So in this formula, I will give you one example like this. This is what? This is methane. I am going to show the structure through methane. H. Okay. So this is the structure of methane, as you can see. So in this formula, solid wedge is used to indicate the bond that is projecting out of the paper. This is for what? This is showing out of the paper. Out of the paper means towards the observer. And the dash wedges, this is the dash wedges, and that is used to depict the bond projecting out of the plane of the paper away from the observer. That is going to be away from the observer, and that is towards the observer, right? So this is the way for showing. The wedges are shown in such a way that the broad end of the wedge is towards the observer. As you can see, the broad end like this. This is the narrow and this is the broad end is towards the observer. So the bonds lying in the plane of the paper are depicted by this when they are lying on the plane of the paper. So this is the way for representing the wedge and dash representation of CH4, and this is the way for representing the three-dimensional representation of the organic compound. Here you can show these two structures are the bonds in the plane of the paper, and these wedges are the dash wedges, and this is the bond away from the observer, and this solid wedges shows bond towards the observer, right? So this is all about the 3D representation of organic compound. Next is the classification of organic compound, and we will discuss this in our next video. So please like, share and subscribe my channel. Thank you.